An integrated gasification combined cycle is a technology that uses a high-pressure gasifier to turn coal and other carbon-based fuels into pressurized gas, synthesis gas. It can then remove impurities from the syngas prior to the power generation cycle. Some of these pollutants, such as sulfur, can be turned into reusable byproducts. This results in lower emissions of sulfur dioxide, particulates, mercury, and in some cases carbon dioxide. With additional process equipment, a water-gas shift reaction can increase gasification efficiency and reduce carbon monoxide emissions by converting it to carbon dioxide. The resulting carbon dioxide from the shift reaction can be separated, compressed, and stored through sequestration. Excess heat from the primary combustion and syngas-fired generation is then passed to a steam cycle, similar to a combined cycle gas turbine. This process results in improved thermodynamic efficiency compared to conventional pulverized coal. Significance: coal can be found in abundance in the USA and many other countries, and its price has remained relatively constant in recent years. Consequently, it was used for about 50% of U.S. electricity needs. Thus, the lower emissions that IGCC technology allows through gasification and pre-combustion carbon capture may be important in the future as emission regulations tighten due to growing concern for the impacts of pollutants on the environment and the globe. This technology is being utilized in a project under construction, located in Kemper, Mississippi. The Kemper project is using lignite coal to produce energy for Mississippians' operations. Below is a schematic flow diagram of an IGCC plant. The gasification process can produce syngas from a wide variety of carbon-containing feedstocks, such as high-sulfur coal, heavy petroleum residues and biomass. The plant is called integrated because the syngas produced in the gasification section is used as fuel for the gas turbine in the combined cycle, and steam produced by the syngas coolers in the gasification section is used by the steam turbine in the combined cycle. In this example, the syngas produced is used as fuel in a gas turbine which produces electrical power. In a normal combined cycle, so-called waste heat from the gas turbine exhaust is used in a heat recovery steam generator to make steam for the steam turbine cycle. An IGCC plant improves the overall process efficiency by adding the higher temperature steam produced by the gasification process to the steam turbine cycle. This steam is then used in steam turbines to produce additional electrical power. Installations: the DOE Clean Coal Demonstration Project helped construct 3 IGCC plants: Wabash River Power Station in West Terre Haute, Indiana, Polk Power Station in Tampa, Florida, and Pinon Pine in Reno, Nevada. In the Reno demonstration project, researchers found that then-current IGCC technology would not work more than 300 feet above sea level. The DOE report in reference 3, however, makes no mention of any altitude effect, and most of the problems were associated with the solid waste extraction system. The Wabash River and Polk power stations are currently operating, following resolution of demonstration startup problems, but the Pinon Pine project encountered significant problems and was abandoned. The first generation of IGCC plants polluted less than contemporary coal-based technology, but also polluted water. For example, the Wabash River plant was out of compliance with its water permit during 1998 to 2001 because it emitted arsenic, selenium and cyanide. The Wabash River Generating Station is now wholly owned and operated by the Wabash River Power Association. IGCC is now touted as capture-ready and could potentially capture and store carbon dioxide. Poland's Kędzierzyn will soon host a zero-emission power and chemical plant that combines coal gasification technology with carbon capture and storage. This installation had been planned, but there has been no information about it since 2009. Other operating IGCC plants in existence around the world are the Alexander in the Netherlands, Puertollano in Spain, and JGC in Japan. The Texas Clean Energy Project plans to build a 400 MW IGCC facility that will incorporate carbon capture, utilization and storage technology. The project will be the first coal power plant in the United States to combine IGCC and 90% carbon capture and storage. Commercial operation is due to start in 2018. There are several advantages and disadvantages when compared to conventional post-combustion carbon capture and various variations, and these are fully discussed at reference 6. Cost and reliability. The main problem for IGCC is its high capital cost, upwards of $3,593 per kW. Official U.S. government figures give more optimistic estimates of $1,491 per kW installed capacity v. $1,290 for a conventional clean coal facility, but in light of current applications, these cost estimates have been demonstrated to be incorrect. Outdated per megawatt-hour cost of an IGCC plant versus a pulverized coal plant coming online in 2010 would be $56 versus $52. And it is claimed that IGCC becomes even more attractive when you include the cost of carbon capture and sequestration. IGCC becoming $79 per megawatt-hour versus $95 per megawatt-hour for pulverized coal. Recent testimony and regulatory proceedings show the cost of IGCC to be twice that predicted by Godel, from $96 to $104 MWh. That's before addition of carbon capture and sequestration, and Sleipner in the North Sea at a commercial scale for the past 10 years. Capture at a 90% rate is expected to have a $30 per MWh additional cost. Wabash River was down repeatedly for long stretches due to gasifier problems. The gasifier problems have not been remedied. Subsequent projects, such as Excelsior's Mesabar project, have a third gasifier and train built in. However, the past year has seen Wabash River running reliably, with availability comparable to or better than other technologies. The Po County IGCC has design problems. First, the project was initially shut down because of corrosion in the slurry pipeline that fed slurried coal from the rail cars into the gasifier. A new coating for the pipe was developed. Second, the thermocouple was replaced in less than 2 years, an indication that the gasifier had problems with a variety of feedstocks, from bituminous to subbituminous coal. The gasifier was designed to also handle lower-rank lignites. Third, unplanned downtime on the gasifier because of refractory liner problems, and those problems were expensive to repair. The gasifier was originally designed in Italy to be half the size of what was built at Polk. Newer ceramic materials may assist in improving gasifier performance and longevity. Understanding the operating problems of the current IGCC plant is necessary to improve the design for the IGCC plant of the future. Keim, K. 2009, IGCC project on sustainability management systems for plant redesign and reimage. This is an unpublished paper from Harvard University. General Electric is currently designing an IGCC model plant that should introduce greater reliability. GE's model features advanced turbines optimized for the coal syngas. Eastman's industrial gasification plant in Kingsport, TN uses a GE Energy solid-fed gasifier. Eastman, a Fortune 500 company, built the facility in 1983 without any state or federal subsidies in terms of profit. There are several refinery-based IGCC plants in Europe that have demonstrated good availability after initial shakedown periods. Several factors help this performance. None of these facilities use advanced technology gas turbines. All refinery-based plants use refinery residues, rather than coal, as the feedstock. This eliminates coal handling and coal preparation equipment and its problems. Also, there is a much lower level of ash produced in the gasifier, which reduces cleanup and downtime in its gas cooling and cleaning stages. These non-utility plants have recognized the need to treat the gasification system as an upfront chemical processing plant, and have reorganized their operating staff accordingly. Another IGCC success story has been the 250 MW Buckingham plant in the Netherlands. It also has good availability. This coal-based IGCC plant currently uses about 30% biomass as a supplemental feedstock. The owner, NUON, is paid an incentive fee by the government to use the biomass. NUON has constructed a 1,311 MW IGCC plant in the Netherlands, comprising three 437 MW STEG units. The NUON Magnum IGCC power plant was commissioned in 2011, and was officially opened in June 2013. Mitsubishi Heavy Industries has been awarded to construct the power plant. Following a deal with environmental organizations, NUON has been prohibited from using the Magnum plant to burn coal and biomass until 2020. Because of high gas prices in the Netherlands, 2 of the 3 units are currently offline, whilst the third unit sees only low usage levels. The relatively low 59% efficiency of the Magnum plant means that more efficient CCGT plants are preferred to provide power. A new generation of IGCC-based coal-fired power plants has been proposed, although none is yet under construction. Projects are being developed by AEP, Duke Energy, and Southern Company in the US, and in Europe by ZAC, PKE, Centrica, E.ON and RWE and NUON. In Minnesota, the state's Department of Commerce analysis found IGCC to have the highest cost, with an emissions profile not significantly better than pulverized coal. In Delaware, the Delmarva and State Consultant analysis had essentially the same results. The high cost of IGCC is the biggest obstacle to its integration in the power market. However, most energy executives recognize that carbon regulation is coming soon. Bills requiring carbon reduction are being proposed again both the House and the Senate. And with the Democratic majority, it seems likely that with the next president there will be a greater push for carbon regulation. The Supreme Court decision requiring the EPA to regulate carbon also speaks to the likelihood of future carbon regulations coming sooner, rather than later. With carbon capture, the cost of electricity from an IGCC plant would increase approximately 30%. For a natural gas (CC), the increase is approximately 33%. For a pulverized coal plant, the increase is approximately 68%. This potential for less expensive carbon capture makes IGCC an attractive choice for keeping low-cost coal an available fuel source in a carbon-constrained world. In Japan, electric power companies, in conjunction with Mitsubishi Heavy Industries, has been operating a 200T IGCC pilot plant since the early 90s. In September 2007, they started up a 250 MW demo plant in Nakoso. It runs on air-blown dry feed coal only. It burns PRB coal with an unburned carbon content ratio of less than 0.1% and no detected leaching of trace elements. It employs not only F-type turbines but G-type as well. Next-generation IGCC plants with CO2 capture technology will be expected to have higher thermal efficiency and to hold the cost down because of simplified systems compared to conventional IGCC. The main feature is that instead of using oxygen and nitrogen to gasify coal, they use oxygen and CO2. The main advantage is that it is possible to improve the performance of cold gas efficiency and to reduce the unburned carbon. As a reference for power plant efficiency, with frame gas turbine, 30 bars quench gas cooling, cold temperature gas cleaning and 2-level HRSC, it is possible to achieve around 38% energy efficiency. With frame F gas turbine, 60 bars quench gasifier, cold temperature gas cleaning and 3-level plus HRSC, it is possible to achieve around 45% energy efficiency. Latest development of frame G gas turbines, ASU air integration, high temperature desulfurization may shift up performance even further. The CO2 extracted from gas turbine exhaust gas is utilized in this system. Using a closed gas turbine system capable of capturing the CO2 by direct compression and liquefaction obviates the need for a separation and capture system. Testing. National and international test codes are used to standardize the procedures and definitions used to test IGCC power plants. Selection of the test code to be used is an agreement between the purchaser and the manufacturer, and has some significance to the design of the plant and associated systems. In the United States, the American Society of Mechanical Engineers published the Performance Test Code for IGCC power generation plants in 2006, which provides procedures for the determination of quantity and quality of fuel gas by its flow rate, temperature, pressure, composition, heating valve, and its content of contaminants. IGCC emission controversy. In 2007, the New York State Attorney General's office demanded full disclosure of financial risks from greenhouse gases to the shareholders of electric power companies proposing the development of IGCC coal-fired power plants. Any one of the several new or likely regulatory initiatives for CO2 emissions from power plants, including state carbon controls, EPA's regulations under the Clean Air Act, or the enactment of federal global warming legislation, would add a significant cost to carbon-intensive coal generation. U.S. Senator Hillary Clinton from New York has proposed that this full risk disclosure be required of all publicly traded power companies nationwide. This honest disclosure has begun to reduce investor interest in all types of existing technology coal-fired power plant development, including IGCC. Senator Harry Reid told the 2007 Clean Energy Summit that he will do everything he can to stop construction of proposed new IGCC coal-fired electric power plants in Nevada. Reid wants Nevada utility companies to invest in solar energy, wind energy and geothermal energy instead of coal technologies. Reid stated that global warming is a reality, and just one proposed coal-fired plant would contribute to it by burning 7 million tons of coal a year. The long-term healthcare costs would be far too high, he claimed. "I'm going to do everything I can to stop these plants," he said. There is no clean coal technology. There is cleaner coal technology. But there is no clean coal technology. One of the most efficient ways to treat the H2S gas from an IGCC plant is by converting it into sulfuric acid in a wet gas sulfuric acid process WSA process. However, the majority of the H2S treating plants utilize the modified clause process, as the sulfur market infrastructure and the transportation costs of sulfuric acid versus sulfur are in favor of sulfur production. Compressed, and stored through sequestration. Excess heat from the primary combustion and syngas-fired generation is then passed to a steam cycle, similar to a combined cycle gas turbine. This process results in improved thermodynamic efficiency compared to conventional pulverized coal. Significance. Coal can be found in abundance in the USA and many. An integrated gasification combined cycle is a technology that uses a high-pressure gasifier to turn coal and other carbon-based fuels into pressurized gas, synthesis gas. It can then remove impurities from the syngas prior to the power generation cycle. Some of these pollutants, such as sulfur, can be turned into reusable byproducts. the other countries, and its price has remained relatively constant in recent years. Consequently, it was used for about 50% of U.S. electricity needs. Thus, the lower emissions that IGCC technology allows through gasification and pre-combustion carbon capture may be important in the future as emission regulations tighten due to growing concerns. This results in lower emissions of sulfur dioxide, particulates, mercury, and in some cases carbon dioxide. With additional process equipment, a water-gas shift reaction can increase gasification efficiency and reduce carbon monoxide emissions by converting it to carbon dioxide. The resulting carbon dioxide from the shift reaction can be separated for the impacts of pollutants on the environment and the globe. This technology is being utilized in a project under construction, located in Kemper, Mississippi. The Kemper project is using lignite coal to produce energy for Mississippians' operations. Below is a schematic flow diagram of an IGCC plant. The gasification